Professor Patrick Das Gupta is a long-time friend and colleague at Delhi University. And his topic is quantum Shardula, measurement problem and gravitational wave detection. Professor Alok Mishra mentioned that Patrick is not quite well, and he has sent a video, which Professor Mishra, please show it to us. Is that Patrick visible? I can see Patrick. I can see a photo of Patrick.
Right. So that's a video that I just shared. So may I start the video?
Yes, please do.
Okay. Thank you so much. Thank you.
Good afternoon, everyone. First of all, I am very thankful to the organizers for enabling me to pay tribute to Professor late Mitra. And today, the topic I've chosen, namely the foundations of quantum theory, is because in the decade 2000 to 2010, Professor Mitra had become greatly interested in the foundational aspects of quantum theory. In fact, I still remember when Professor Roger Penrose was visiting Delhi, there was a meeting organized in the India International Center, and there Professor Mitra talked at length about the foundational aspects of quantum theory. Now, we all know that this meeting was very important because, one had to pay the tribute to one of the outstanding theoretical physicists of India, namely Professor Mitra. And I'm really thankful to the organizers like Alok, Gargi, Professor Haridas, and many others, and in particular Alok, who had taken a great deal of efforts to make this meeting a great success. Now, let me begin my talk. Shardula in the ancient Indian context is essentially superposition of several distinct animals, and they are found in paintings and as well as sculptures like this one, where you can see the head of an elephant superposed with the body of a lion, and such Shardula figures are very common in many of the sculptures of South Indian temples. And we all know that in quantum theory, one indeed talks about superposition. For example, in the celebrated Schrodinger cat problem, we know that there is a whole system of counters, the 60 nucleus, as well as living systems like cat. In effect, you have an entangled state where one of the states, which is in the product state, is the cat dead state entangled with another cat alive state. And that is the reason I talked about Shardula. And one of the celebrated problems, an outstanding problem indeed in quantum theory, is that when we observe, the state collapses. So either we see the cat dead or cat alive in such a configuration. The question is, what leads to this collapse? We know that when you have a quantum system which is evolving on its own without any intervention from any measurement apparatus, the state evolves according to the Schrodinger equation, IH bar d by dt acting on the state is equal to the Hamiltonian operator acting on the state, and this evolution is completely deterministic. However, the postulate, the fourth postulate of standard quantum mechanics says that if I want to measure the observable A, eigenvalues are an and eigenstates are un corresponding to eigenvalues an, and when we observe the quantum system using a measuring apparatus, then in general, the probability that we observe one of the eigenvalues an, that probability is given by the Born rule, namely the mod square of the inner product between the eigenstate un and the quantum state. However, we all know that a measurement is nothing but an interaction between apparatus and the system. Apparatus is also quantum mechanical, and therefore the interaction should be described by an interaction Hamiltonian, and the apparatus plus system should evolve according to the Schrodinger equation, where the Hamiltonian is nothing but the Hamiltonian for the apparatus, plus the Hamiltonian for the system, plus the interaction Hamiltonian. And the whole system must evolve in a deterministic manner. But why should we get the probabilities which are indeed what is seen whenever there is an observation? Where does the probability come from? One of the key things to sort of highlight is that whenever you use the usual unitary evolution, one sees the entanglement between the states of the system and the apparatus. And you have different branches in which the pointer state and the quantum state, they are entangled with each other, and different branches corresponding to the different eigenstate of the system, the branches don't talk to each other. The other key factor is that during the interaction between the apparatus and the quantum system, at the detection level, one finds, and this is something very general, that the few degrees of freedom of the quantum system interacts with innumerable degrees of freedom of the apparatus. And of course, this is the origin of the increase in the entropy, because unless you keep track, you don't know which are the degrees of freedom of the apparatus of the pointer state which has got influenced by the interaction when there is a collapse. Now, in this talk, I will share some of my thoughts regarding what could be happening and could these ideas at some point of time explain the origin of the probabilities. The first thing is, let's ask a question. After all, gravity is universal, and when one takes into account the quantum theory of gravity, we know that there are the Planck numbers, Planck mass, Planck length, Planck time. They give us some limitations to the ideas of classical general theory of relativity. Here one can ask, is there a Planck number of degrees of freedom? Because here we see that a large number of degrees of freedom are involved in the apparatus that gets entangled with the quantum system. So if one takes the Planck mass, which is about 10⁻⁵ gram, and divide by the electron's mass, then one gets the number 10⁻22, which is very close to the Avogadro number, which is a hallmark of macroscopic systems. And of course, the reason I've chosen the electron mass is because most of the detectors in the apparatus they essentially contains of atoms which has electrons and protons. If one chooses proton, the number will come down to about 10 to the power 90. Now, the idea that I would like to sort of stress on is that we know that there is, from quantum theory, there is a number phase uncertainty. Now, could it be that when the detected degrees of freedom exceeds the so-called Planck number, some kind of fluctuation in the phase, the random fluctuation in the phase, could it be the origin of the probabilities? Now, here one should also stress on the fact that when the quantum system is interacting with the apparatus, the measurement timescales are very short, and therefore the amount of energy exchange between the quantum system and the macroscopic apparatus, that energy will be uncertain, which will be given by the energy time uncertainty. And such fluctuation in the energy of exchange, according to general relativity, would cause metric fluctuations. And metric fluctuations will lead to fluctuation in the proper time. After all, the evolution of the state, one would think that it's the proper time which should be more relevant than the laboratory time. And fluctuation in the proper time can cause phase fluctuation. So the number, the Planck number, and the relevant phase fluctuation resulting in such random number, could it be the origin of the probabilities? To highlight a typical measurement scheme, namely the spin measurement using a Stern Gallic apparatus, we know that the real measurement takes place when the entangled state wave function telling the trajectory of the electron going towards the top part entangled with the spin down state, and trajectory telling us the apparatus, the electron's spatial wave function evolving towards the bottom part, direct product up state. The final measurement takes place when the electron interacts with some detector system like a photographic plate, etc. And there, after the interaction with the detector state get deep, so which is composed of innumerable number of atoms, different atoms get excited, and these atomic excitation, there is, because of uncertainty in the energy, there'll be uncertainty in the phase, there'll be fluctuation in the phase that can lead to random phases. And could it be the origin of the probabilities? And this can be generalized to any arbitrary quantum measurement using the kind of interaction Hamiltonian, which is a product of the quantum variables and the operator. Supposing one wants to measure the position of the quantum system, then one can have a interaction Hamiltonian that couples the position operator of the quantum system with the pointer momentum states, and one can easily show that such an interaction Hamiltonian would be useful in reading out the position, but the final state is still an entangled state, telling us that when the pointer position is GT,
Hari, what's the problem?
the quantum position is x1, and so on.
Are you listening me?
Reading the pointer variable, one knows
Professor Haridas.
Electron, but still the whole system is entangled. When does it? How does the mod C1 square, mod C2 square, etc., as probabilities arise? So one of the thing is, as I'm highlighting, that probably the unitary evolution should be recast, that this T must be replaced, not the laboratory time must be replaced. The individual branch should evolve according to the corresponding proper time. So the and whether that could lead to the so-called bond probability. Of course, the gravity-induced collapse have been talked about by Giossi, Penrose, Ciano, and many others. And there are other many worlds interpretations, etc. But the main problem is in the many world interpretation, the branches, different branches, they don't talk to each other because they are happening in the Hilbert space. And the many world interpretation also doesn't, unless you use decoherence and averaging over the environmental states, then one doesn't get the bond rule, namely the mod square of the individual coefficients in the linear expansion. So in the many world interpretation, yes, all the branches occur, but the branches don't talk to each other. Is there a way we can make the each of the branches in the many world talk to each other through this random phase so that one gets the bond rule? Of course, I mean, the solution to the problem requires much harder work. The question is, can we sort of think as to what could make different branches talk to each other? I'll skip some of the slides. Let me try to highlight by using a thought experiment, trying to exaggerate the role of gravitation here by taking the final detector to be fairly, 1 milligram masses. So imagine that our detector is nothing but 2 blocks, 1 milligram weight reflectors, which is essentially in an unstable position. So we have 2 such unstable equilibrium 1 milligram reflectors. And let's say one has a photon, a single photon state interacting with a half silvered mirror, so that the state now is a superposition between 2 states, 2 orthogonal states. That is, the state is Cn1 plus C2N2 after interacting with the half silvered mirror. And according to quantum mechanics, after the interaction, we have the state Cn1, N2, psi1 becoming psi1 star, namely the 1 milligram falls off after being hit by the photon, plus C2N2 and psi2 changing to psi2 star after being hit. And it will be an entangled state. But the key thing to realize is gravity is universal. Gravity cannot be screened. The whole problem when this psi1 is in transit to becoming psi1 star, there is the gravitational potential is changing, and due to that, proper time is changing here, and this proper time changing, the fluctuation, gravitational fluctuation will also affect the other bob. Similarly, this bob in the other branch changing to psi star, falling, its gravitational potential will also affect psi2 star, psi1 into psi1 star. So in reality, the time evolution will develop the following kind of a system. It will be C1 N1 prime, namely after hitting the state of this branch of the photon will change, psi1 star, and the time involved, the time will depend upon not only psi1 star but also psi2 star. And this whole branch, as you can see, you got the psi1 star depends upon psi2 star, and psi2 star depends upon psi1 star, and the time itself depends upon both the branch. So in other words, what we see is that if we really take into account the proper time into consideration, then the 2 branches are actually talking to each other. And because gravity cannot be screened, and no matter what kind of detector you use, whether it's a photographic plate, the particles in the top branch, they share the energy, and there's a lot of fluctuation here. The gravitational fluctuation will also influence, however tiny it is, will also influence the particles, the detecting atoms in the other region, because in no way gravity can be screened. And therefore, this cross-talking would essentially bring about a nonlinear evolution. And perhaps, and we know that there are ways, if you modify the Schrodinger equation by using certain nonlinear terms, you can indeed get the Bond rule. For example, the Gregorian-Coase paper in 1995. So indeed, the gravity can bring about a nonlinear problem. Since the time is limited, I will skip some of the slides. I will come to the end part, namely the fact that the metric is the GR metric should also be described in quantum mechanical way. The question is that can we test whether the GR metric is indeed quantum mechanical? Here, a host of authors, starting from Amelino Camellia in 1999 to Dyson, the 13 and recent work of Parekh, Wilczek, and Zaharia, they have all talked about if one takes the quantum state of the gravitational wave, how does the geodesic deviation, namely the separation between two freely falling particles, gets affected? And after all, the LIGO detectors are nothing but the two mirrors, are nothing but freely falling test particles. And these work shows that in principle, the geodesic deviation will have random fluctuation, and such a thing would appear as a noise in the LIGO detector. And depending upon, of course, the quantum state of the gravitational wave, impinging gravitational wave, the noise will have different form. And in principle, therefore, LIGO detectors can be used to check whether gravitational wave indeed they are in reality quantum states, because there are a minority view that perhaps the geometry and metric, they should not be quantized. There's a lack of time. I must stop here. It's unfortunate that because of certain limitations that I'm out of India and I've been traveling and I have serious limitation with internet. I'll stop here, and if there are questions, they can be sent by email to me. Thank you for your patience. And this is a picture from the paper by Parekh, Wilczek, and Zaharia, where they have computed what kind of fluctuations arise between two freely falling particles when a quantum gravitational wave impinges. Thank you very much.